Now that we're on the same page of describing atoms and most importantly their nuclei, we want to talk about nuclear stability.
All right, so what we want to start to talk about is why nuclei exist and which nuclei are stable. So on face, it actually doesn't make any sense for a nucleus to exist how it does, right? It's a bunch of positive and neutrally charged particles jammed in together. And like charged particles repel each other. So there is an intense amount of repulsion between all of the protons that are held together in a nucleus. So there's, all these positive charges. That positive does repel, and they do not want to stay together. So any nucleus has an intense amount of repulsion that those protons want to move apart. So what holds them together is something that's called strong force. So the strong force is also called the color force. That's why there are colored rainbows in this diagram right here. The arrows are rainbow colored. So this is a unique force. It doesn't exist outside of nuclei, where nucleons, which are protons and neutrons, want to be close together. It's called strong because it's a strong force because it's very strong. There's an intense amount of attraction holding nucleons together. So this word nucleon basically just means any particle that lives in a nucleus, so protons and neutrons. And so this is an attractive force between protons, but it's really, really short ranged. That's why nuclei are really small and really dense, right? They're really, really packed in together. It's a very small mass of the whole, or small amount of volume of the entire atom. So those positive charges are pushing each other away, but all of that strong force is holding it together. And one of the important things about it is that the repulsion is only between protons, but the strong force is between both protons and neutrons. All of them just want to be together in that nucleus, are held together with that strong force. Okay, so with these two kind of ideas in mind, that you have some inherent large amounts of repulsion from positive charges and then that strong force holding it together, we can actually plot out which nuclei are possible. Okay, so there are only certain combinations of protons and neutrons that correspond to what are actually stable nuclei. Okay, so this graph over here is demonstrating what's called the band of stability. So each of those black dots on that graph correspond to a number of protons and neutrons that is stable. What we mean by stable is that if a nucleus with that combination of protons and neutrons does not fall apart. Okay? There are only 252 known stable nuclides. Okay? So that's across 80 elements. There are 80 elements that you can create a stable nuclide of that element, or that a stable nuclide exists. That those nuclides, they just exist and they won't fall apart. The reason why a nucleus would fall apart is because of that positive repulsion. It just doesn't hold itself together correctly, doesn't have enough strong force to kind of overcome that, and so it just ends up falling apart. And so those black dots are showing those are the only 252 known combinations that are stable. It is potential there's ones we haven't found, that they'd be in small amounts, or say another, not on planet Earth, but we don't have, there's just those here. And anything else, if a nucleus were to exist outside of those black dots, outside of what's called the band of stability, it will be unstable, and that nucleus will want to fall apart. I'm going to want to not be a nucleus anymore, a single nucleus at least. So if we kind of plot out, there's a very narrow band of stability, right? Those black dots. There's a lot of other possible combinations of protons and numbers of protons and neutrons that don't work, that are unstable. And there are three main motivating factors as to why a nucleus would be unstable. The first one is that the nucleus is too big. Any nucleus with more than 83 protons is unstable. 83 is the cutoff, that's bismuth. Bismuth is the largest element that has stable nuclei. When we mean stable nuclei, that those nuclei will never fall apart. They are always going to exist. The other possibility then is if you're small, okay, so 83 or fewer protons, but the neutron to proton ratio doesn't work out, right? So we can see that this band of stability, right, that those black dots are going out in a line, basically, and anything below that would be where there are too many protons relatively, or not enough neutrons to balance it out. And then above that, we'd have a region where we have too many neutrons. So in that case, the nucleus is unstable because it's too many neutrons. So this is kind of like a Goldilocks kind of thing. You got to get it just right. When you're adding in protons and neutrons into the nucleus, you got to get it just right to how many are in there, right? You don't have too many protons, don't have too many neutrons, got to get it right in the middle. And it is fairly sensitive, right? There's not a ton of combinations that are possible that actually are stable. So let's talk about these different ideas. So this idea of being too big, our cutoff is 83 protons. So if you have 83 protons, it's possible to be stable. Any nucleus that has more than 83 protons is definitely unstable. And what just starts to happen is as the nucleus gets bigger and bigger, has more and more protons, it has particles, it just becomes a physically larger object. Right? In much the same way that atoms have different size, the nucleus is still very, very small, but it gets relatively larger for all the nuclei. So you can imagine there are now protons that are on opposite sides of that nucleus. And that strong force, that color force that holds the nucleus together really is very, very short ranged, right? A couple of these nucleons across. And so what ends up happening is you have these protons that are on, say, opposite sides of the nucleus. They don't have any attraction. They are purely repulsion. And so when you get to these bigger and bigger and bigger nuclei, it's just impossible to overcome all of that repulsion that starts to grow. And so the nucleus has to be unstable. So these large nucleus, anything that has more than 83 protons has to be unstable. It doesn't matter, just because it just becomes so much positive charge in there that it just can't handle it, and it would have to be unstable. So another thing that always causes instability is any nucleus with more protons than neutrons. Okay. Again, this idea, the protons are just contributing repulsion and some attraction. Neutrons kind of work like a kind of a glue to hold everything together. The neutrons are neutrally charged, so they don't repel each other, but they do have that sort of attraction that holds everything in. So they do contribute to that. So there are only two nuclides that are stable that have more protons than neutrons. One is just a hydrogen 1, which is a single proton, so it has 1 and 0, so it can't really fall apart. It's just a proton as is. The other one is helium 3. So helium 3 is the only nucleus with neutrons, or more than one proton, that has it's 2 protons and 1 neutron, and that is stable. That is the only exception to this. Everything else, and in general, when we're looking at this, if we have more protons than neutrons, we can see this space is empty. There is no black dots in here. So that line is tracing out the 1-to-1 ratio, basically, and above that would be more neutrons than protons. Below that would be more protons than neutrons, and there's nothing down there. So we can see that when it comes to neutrons, we can have more neutrons than protons, and we kind of actually need to. We can see that this curve goes up away from the 1-to-1 line, and so you need more neutrons, but there's still a limit to how many. So for small nuclei, so that would be like, say, atomic number 20 and below, so calcium and below, neutrons and protons are almost equal. You would expect, you would have maybe 1 or 2 extra neutrons, but not more than that. You're going to be really close on it. And as the nuclei get bigger and bigger, you can see there's more neutrons than protons, but not by a lot. It still is relatively close. As you get to the more extreme ends, you approach 50% extra neutrons. But for the most part, it is not that many more neutrons in the nucleus than there are protons. The ratio is going to be relatively close, but there is an upper limit. You can't have too many neutrons in a nucleus. It is that goal, got to be just right. Not too little, not too many. So when it comes to figuring out which ones are stable, we're going to kind of cheat. We're going to use results that come from what isotopes of an element exist. And that is from that averaged atomic weight, right? Isotoped average atomic weight. If you look on the periodic table, you're given an atomic weight. So for copper, for example, it's 63.55. That 63.55 number is representing the fact of if you average which isotopes are common of the element and you average their different masses. And so when copper, what it is, the stable isotopes are copper 63 and copper 65. And so you always have 29 protons in copper, and then the 34 and 36 neutrons are stable. And so what you're looking at when you're looking at, is this particular nuclide stable, you generally want to look at, well, is it close to whatever the atomic weight is? You can get that number off the periodic table. If your value is close to that, then you're good to go. So, that's kind of that idea. But we want maybe a little more information. So, if we were just looking at numbers, 63.55, we would probably think carbon 60 or copper 64 is stable, but it's not. And the reason we can tell that it's not is because the number of protons, 29, and the number of neutrons, 35. Both of those are odd numbers. When you're building up nuclei, even numbers of protons and neutrons lead to stability. So when we're looking at this, we can see that the copper 64 is close, but it does have odd numbers of protons and odd numbers of neutrons. There are only 5 nuclides that have an odd number of protons and an odd number of neutrons and are stable. They are generally all small. Anything that's big, if you have double odd, it is definitely unstable. So even numbers of things tend to have more stability, even numbers of protons and even numbers of neutrons. One of the manifestations of this is if we kind of zoom in on the band of stability, you can see that it's not even it's not even between atoms that have more or less stable isotopes. So we can kind of see there's kind of a stepped nature. What that stepped nature is implying is that basically every other isotope, so every other element has more isotopes. Elements with an even number of protons are easier to make stable isotopes of, right? Because you already have an even number of protons, the neutrons cannot be odd then. If you have an odd number of protons, it is more difficult to generate a stable nuclide because the protons are odd. So the neutrons have to be even, and that really restricts the possibilities. So that's why you can see what this is, because each line on this graph, right, corresponds to a particular number of protons. That corresponds to a type of element. So that type of element has, particular stabilities, and it's going to be, you'll see that step up corresponds to more possibilities for a particular type of element. So you can see, and you also see something like, if you look on this 50 line right here, that's this settled line, you see there's a ton there. That's tin. Tin has 50 protons, that's very even, and it has a ton of possible nuclides that you can form from it because your neutrons have a ton of different possibilities. You can see again, even number, a lot of possibilities, odd number, one possibility, even number, a lot of possibilities, odd number, one possibility, and it alternates back and forth, between that even odd. Because that's just number of protons, and that's going to affect your stability or inform stability. All right, so we can put all of these information together in terms of parsing out whether or not a nucleus is stable. And so, one of the things we first always want to look at, the easiest thing to determine, or kind of cleanest thing, is the atomic number above 83. If it's above 83, it's unstable. It doesn't matter. You don't need to kind of get into the weeds or kind of making guess and check sort of assessments. So this one, if the atomic number above 83, it's unstable. If it's smaller, then you have to look at that neutron-proton ratio. And so, you're looking at that atomic weight. Look it up on, just use the periodic table, use isotope information kind of cooked in. Is it close to that? Is it within, say, plus or minus 1? The closer it is to that, the more likely it is that that's stable. If the mass is higher, so if the mass of the nuclide you're looking at is higher than that atomic weight of the periodic table, you have too many neutrons. If your mass is lower, you have too many protons. What you're looking for, higher than that weight, or lower than the weight. The plus or minus 1 rule is a little harder to parse out. In our case, then you can ask, are they even? Are your number of protons even? Is the number of neutrons even? Both of those things help with stability. I don't want to worry too much about getting into the weeds of figuring out which specific nuclides are or are not stable. What we want to be able to do is parse out stability for being too big. If the mass of the nuclide is higher than the atomic weight and we're told it's unstable, that means there's too many neutrons. And if the mass is lower, it has too many protons. So that's what we really want to kind of focus on being able to parse out. A lot of times you're going to be told this is unstable. Why is it unstable? And you want to be able to answer one of those three choices. It's too big, too many neutrons, or too many protons. So along those lines, predict why each of the following nuclides is unstable. Again, we don't need to get into too many of the weeds of like even, odd, parity kind of stuff. I'm going to tell you this is unstable. Tell me why. Okay. So I have the first thing I'm looking at is this fluorine, and I'm given the symbol. I got fluorine 22. 9 is the atomic number of fluorine. So I want to parse out, whenever I'm looking at an atomic symbol, I want to parse out the information, what's in this nucleus. So 9 is the atomic number, 22 is the mass number. So that's protons and neutrons. I do some subtraction there to find out that I have 13 neutrons. So 9 protons and 13 neutrons. So this is definitely not too big. 9 is way below 83. I'm just looking at the number of protons. It's definitely small enough. This molecule or this nucleus, not too big. It's not unstable for that reason. So then I need to look at the atomic weight, and I'm going to pull that off the periodic table. So fluorine's atomic weight is 19.00 AMU. Okay, so that would mean that the stable isotopes are on average close to 19 for a mass number. I'm at 22 in this case, and I am 3 AMUs away. Especially when I'm looking at something that is small, right? I only have 9 protons in this. This is a small nucleus. 3 is a pretty big gap. Also, the Z is odd. At 9 is an odd number of protons. 13 is an odd number of neutrons. All of those things point to this being unstable. And the reason why is that I have too many neutrons. So all those signs point to instability, and the instability that I would really factor in is the fact that this 22 is greater than the 19. There's too much stuff in this nucleus. I know it's fluorine because it's 9 protons. My mass is too high for fluorine atoms. It has to be because of the neutrons. I have too many neutrons. Let's take a look then at my second one, thorium. So in this case, 90 is my number of protons, and then 231 is going to be the protons plus the neutrons. So I can do some subtraction. I have 90 protons and 141 neutrons. Whenever I see a big number like this for protons, 90, that is bigger than 83. This nucleus is too big. This nucleus is too big. It's not going to be stable just because it's too big. And I know that it's because it's too big. I don't need to think about the atomic mass. I don't need to look at any of that stuff, any information about thorium on the periodic table. As soon as I see an atomic number greater than 83, that is an unstable nucleus because it's too big. Chromium 54. The 24 is the number of protons. Sorry, 45 is the neutrons plus protons. So I do some subtraction. This has 24 protons and 21 neutrons. All right, it's not too big. 83 is my cutoff. 24 is well beneath that. I can see it's not too big. One of the things, chromium is an element you've heard of. If you've heard of it, it's probably not too big. If you've used it in the lab or seen it or know its applications. Most of the big ones, if the nucleus is unstable, that really limits its applications. So thorium, TH, is probably not something you'd heard of. Chromium is something you've potentially touched. That's a good sign. It's probably not too big. There are versions of it that are stable. So back to chromium though, it's not too big, so we need to look at the atomic weight. It's 52 if we look at the periodic table. 45 is 7 below 52. This thing is way too small. There is not enough mass in there. There are too many protons. We can see that mass, another way to say that would be that there's not enough neutrons. There's too few neutrons, but generally we do say it's too many protons because of when we talk about how it's going to respond to it. So we can parse out, we can look at that. The other thing we could have seen is if we also just looked at it, another big red flag, I have more protons than neutrons. 24 is greater than 21. We also could have stopped right there. When we see a situation like that, if I have more protons than I have neutrons, that has to be unstable, except for that helium case. But this is chromium, so this is very unstable.
Participation 417, question 1. Predict why each of the following nuclides is unstable. I got the PO210 and the SC41. This is the first question on participation 417, due Friday, April 17th, over on Blackboard. The link to the assignment is right below the document where these videos are posted. Again, predict why each of the following nuclides is unstable. We've got the polonium and the scandium there. Okay, got our first question on participation 417. We're also halfway through this set of videos. Not too many videos. They are on the long side, some of them, but not too many videos here. I'll see you in the next one.